Okay, chapter 7 is about impulse and momentum. Um, Two things that we have not talked about, obviously, up until this point, although maybe in high school you may have come across these things. Um, okay, impulse momentum theorem. Um, when your force tends to vary, your calculations get a little tricky. Most of the time, there are not a lot of instances of a constant force out there, whereas your force varies. Think of a football player pushing the sled. Obviously, your force is going to change throughout the process. So, we instead are going to look at the average force in the time of contact to get something new, J, which is impulse. So, there we go here. So, J stands for impulse, and that is measured in two things. It could be either a kilogram meter per second, or in the case of force times that, a newton second. Or, oh wait, that's an and. Ha! Or. So one or the other. This is generally the preferred unit for impulse. But basically, what impulse tells you, it tells you the average force and how long that force is applied to an object. There's not really a proof. It says proof, but basically, we know that force, the average force, let's say, is mass times acceleration, and then that is times the change in time. Ugh, that's really bad. Let's try this again. Change in time, and then that's equal to J impulse. Well, what is acceleration? Acceleration is nothing more than the change in velocity over the change in time. Change in time is still there, and I'll put this in parentheses to say, hey, I made a substitution, and then that's still equal to impulse J. And then notice your delta T cancels out. So impulse is also equal to M delta V. This is what's known as your change in momentum. Why change? Because it's the change in velocity. So if you know the mass of an object and the change in velocity of that object when it impacts something like a baseball being thrown at a bat that's bunting, it will have a change in velocity, and then you'll know the mass, and you can use that to figure out not necessarily the force, but the product of force and the time of the collision. And then if you know the time of the collision, then you can actually calculate the force. Instantaneous momentum, if I can find my little cursor here. That's simply P is equal to mv. So P is also known, or rather is known, as momentum. J is impulse. P is for an instantaneous momentum, whereas J is for a change in momentum. So that's the big difference between the two. We will utilize instantaneous momentum later on in the chapter, but I'm just introducing it now so you kind of have an idea. So it got cut off. Well, we could still at least read it, but that's sad. Sorry about that. A pitch, let's do a baseball example. So a pitch is thrown at 30 meters a second, and the ball is hit with a velocity of 50 meters a second. If the mass of the ball is 240 grams, then what's the impulse on the ball from the bat? And if the collision lasts 30 milliseconds, then what is the force felt on the ball? Okay, so kind of draw a really pretty picture here. So basically, you have a baseball player, and he's really hitting the ball in a weird way. I know, but work with me on this one. So we know that the ball is traveling to the left at 30 meters a second, and then it leaves at 90 meters a second. So our impulse is what it's asking for, J. And so when it asks for what's the impulse on the ball from the bat, so it's from the bat's point of view. And really, when you look at it from the point of view of that, you just look at the change in velocity. And so in this case, I have mass delta V. The mass of my ball is 0.24 kilograms. The change in velocity is where you have to be careful. It goes a final velocity of 90 to the right, which is positive, minus the initial velocity of a negative 30 to the left. So you got to be careful with that. Whenever it changes direction, it's going to have an overall larger change in velocity than in any of the individuals that you started with. So that gives me 120 times 0.24, and that gives me 28.8 kilogram meters per second. Okay. Or I could say Newton seconds, and so that is at least the impulse, which doesn't make a lot of sense. So then we can figure out, well, what if we have a collision time of 30 milliseconds? Well, that's where we use the fact that this is equal to J, right? And we also know that J is equal to F delta T. And so I take my 28.3 kilogram meter per second, and I multiply I set it equal to the average force. Sometimes I'll just put F, and I really should put F average. I apologize. And then 30 milliseconds. So a lot of collision times aren't going to be very long, so pay attention to the time. That's a millisecond. Milli is 1/1000th of. So it's actually going to be 0.03 seconds to find that collision time. So I take my 28.3 and divide it by 0.03, and I get 943 newtons, which is quite a lot of force. Probably too much for what I did, but it works. And while I didn't explicitly say it in the problem, I'm really just looking for the magnitude of the force. Meaning I don't care about direction. I will in the next one. Maybe I'll change that. I need to change that in the future. So, if an object is changing directions, then it'll be the change in velocity is going to be greater than the absolute value of any of the first numbers. All right, well, let's look at a water droplet. So a 1 gram water droplet is absolutely massive and probably not realistic, but I wanted to use at least a number that was easy. I suppose it's possible, just not very likely. It falls in the sky, and the terminal velocity of the raindrop is around 13 meters a second, meaning at that point the lift or drag force from the air is equal at least to the weight, and the object no longer accelerates. It still falls, but it falls with a constant speed. So basically, we know that what would be the force felt on one's head if the collision time is 10 milliseconds. So did I give myself an extra page? I did not, but I can work with this. All right, so we have, just going to write it as F, AVG, delta T is equal to M, I don't know what I was doing right there, M delta V. And we know the mass of the droplet. We know, we need to figure out the change in velocity. So let me write this out a little bit. So basically, a raindrop is going to stop on impact, right? So it's going to go down at 13 and then be stationary at 0 because raindrops, literally just stop on your head. And so let's do this. Okay, so that gives me F average, is what we're looking for. The change in time is going to be 0.01 seconds now. The mass is going to be, it's in grams, so 0.001 kilogram. Change in velocity, the final is going to be 0, but the initial, it went down, so down is negative, so I say minus a negative 13, since down, we recall, is, negative. And so it's just going to be 13 for the change in velocity. And so I just take 13 times that by 0.001 and divide that by 0.01, and I get 1.3 newtons. It's a large force for a raindrop, but... Okay, so it's asking, though, specifically what would be the force felt on one's head. So since we call down negative, which should be a negative 1.3 to account for, that's the force on from the droplet on someone's head. Positive 1.3 would be the equal and opposite force going up. So, now let's do the same thing, assuming no loss of energy, and the same collision time and mass. Find the force if it's an actual ice pellet. And a hailstone's terminal velocity is around 19. Or, well, it depends on the size of it, to be honest with you, but 19 is a reasonable value that I looked up. Okay, so we're going to do the same thing. We have the same time, so 0.01 seconds. The same mass, 0.001 kilograms. We're assuming it rebounds at the same speed, assuming no loss of energy. So that means it's going to rebound. So instead of 0, it's going to rebound at a positive 19. And then the initial is a negative 19 as well. And I did not include two parenthesis brackets. That's probably what you're thinking, right? That's what I'm thinking. That's what I'm thinking. So that's going to give me 38 times 0.001. Divide that by 0.01, and that gets 3.8 newtons. So yes, a piece of ice is solid, but fundamentally, even if it's the same mass, just because it's a hailstone and it bounces, it's actually going to impart more force. And once again, this is actually a negative to account that it's going down. Ooh. The magnitude of the force would be 3.8. But the point of this is, I just want you to know that anytime something bounces, it's going to have a lot more force than if it just stops on collisions. So a key here is, if you're ever designing something like, I don't know, and I'll talk about this later, like a roadblock, you kind of want to slow it down. You don't want objects to bounce because it's going to be a lot more force. Okay. All right. Here we go. So, all right, we've got a 1,050 kilogram Toyota Yaris traveling around 75 miles an hour, 34 meters a second. The car hits a patch of ice, slams directly into a parked school bus, taking 2.33 seconds to come to a complete stop. We want to figure out the average force exerted on an 80 kilogram driver and the acceleration in terms of G of the driver. Okay, so we don't know much about the school bus, but that's not relevant. Right now, we do know that we need to figure out the average force. And so remember that F average delta T is equal to M delta V, our impulse momentum theorem. We're looking for F, which will come up later. Our change in time is 2.23 seconds, so reasonable with time there. Mass is going to be the mass of our car. And there is a passenger in there, because that's going to matter too. So plus 80. And we assume it comes to a stop. It doesn't really matter how I want to do this, but we'll say it was coming from the left. So 0 minus a 34. You could say 34 minus a 0 if it's coming from the right. Either way, the change in velocity, the absolute value should be 34 in this problem. Okay, I need to figure out average force. Let's do it. Let us do it. All right, so we have 1050 plus 80 times 34. And then I divide that by 2.23, and that gives us a force of 17,229. Okay, and so that answers our average force. And then what if we want to know the acceleration in terms of G? Well, to figure out the acceleration, if you recall, acceleration is nothing more than force divided by mass. So I'll take my 17,229 newtons and divide it by the mass of my driver. And I get 215.4. And a lot of times you try to calculate in terms of G or 9.8. So for every 1 G, it's 9.8 meters a second squared, so I can cancel that. So I'm just going to divide that value by 9.8 and give me around 22 Gs. That is enough to kill you, although there have been humans that have survived higher Gs than that. I think there's a picture at the Cosmosphere of a guy in some sort of sled, and I feel like he was in his 20s. Like, he got into the 20s of Gs. I can tell you, Peregrine Falcon regular experiences in the 20s of Gs through the dive bomb. But, anywho, so 22 G forces. On contrast, if I wanted to find the acceleration of the car, I would divide that by 1050, and I would get a much smaller acceleration, which makes sense because this passenger is, if they're not in a seatbelt, they're probably going through the window, right? And the car, well, the car's going to move, but not nearly as much as the passenger, which makes sense. The force is the same. Everyone's experiencing the same force. What they're not experiencing the same thing as the acceleration because their mass is different. That brings us to our next problem. The school bus, we're going to look at that. Let's say it's around 16,000 kilograms, and I believe I looked this up at one point, and that's around half full of kids, roughly. We want to figure out the change in velocity of the bus. So I'm going to use my force from earlier because it's equal and opposite forces, right? So it's 17,229. So we know our average force. We've got that. And we also know our average, well, we know our change in time, of the collision. Our impulse is actually the same, but we never calculated it. Not completely. And so I'm going to use the impulse momentum theorem again. F average delta T is equal to M delta V. And so I take my large average here, 17,229 newtons, change in time of 2.23 seconds. Mass is around 16,000 kilograms, which seems really high, but I believe I looked that up. 15,000 pounds. It depends on how much you got, but and change in velocity. So we're going to solve this for delta V. So I take my 17,229 and I multiply that by my 2.23, and then I divide that by 16,000 and I get 6.58. So the change in velocity of the bus is going to be 6.58 meters a second. Recall earlier that the change in velocity of my Yaris was 34, absolute value. And so that makes sense. It's kind of like a big, semi-truck hitting a small little Pinto or smart car. Smart car is going to get demolished and the truck's not going to feel much of it. Same thing with a bus. That's generally why they don't have seatbelts, because even if they do get in a wreck, they're just so much bigger that it's hard to move them. They've got so much more inertia. And so its change of velocity is rightfully so a lot smaller. Okay, next up is the principle of the conservation of momentum. It's actually the principle of conservation of linear momentum, because there is one for angular momentum we'll get to later. But basically, it's the total linear momentum of an isolated system remains constant and is conserved. Note that these are capitals. Capital P's rather. What this really means is that the sum of all of your initial momentums is equal to the sum of all your final momentums. I.e., you would have m1 v01 plus m2 v02 ... equals m1 vf1 plus m2 vf2 there we go ... means we could have 300,000 different objects operating in our system, so to speak, but you're only going to have like 2-3 tops. 2 is really, I think, the highest actually you go. Um, so this right here, this M1, this is just P naught 1, little p. This is P naught 2. This is PF1 plus PF2. So you can think of it as, let's say you have a pool ball or a little ball. We can call it an 8 ball because the 8 ball is black, right? I think so. And that 8 ball goes and hits a 1 ball. Let's make it a stripe. Okay, I don't think the 1 ball striped. 2. I don't know. The point is, if you know the initial momentum beforehand of the 8, well, let's label this 8 and 2. If you know the initial momentum and the final momentum of the 8 ball, and if, let's say you just know the initial momentum of the 2 ball, you can figure out the momentum of the final momentum of the 2 ball, given that you have all the other information. So this works in a lot of collision type problems where you have lots of different objects interacting with each other, and as long as you know its mass and velocities, you can usually use it to figure things out. We're going to use this on the next problem. Well, first we got to talk about collisions. Then we'll use it on the next problem. Sorry about that. So collisions in one dimension. There are really 3 types of collisions and 2 that we really deal with. There is elastic collisions where kinetic energy is conserved. This is like a billiard ball example. Write that up here. Billiards is the common usage of elastic collisions. It's used a lot in particle physics and actual applications. Sometimes your kinetic energy is conserved in particle physics, depending on the situation. But in any case, this is where your kinetic energy is conserved, meaning your energy that you start with is going to be the total energy that you end with. So the kinetic energy is conserved. Now, an inelastic collision is where kinetic energy is not conserved. Most collisions are going to be inelastic. We usually approximate a collision and call it elastic. For example, the billiard ball, the kinetic energy is not completely conserved, meaning there's going to be some loss of energy due to like friction. But we generally will call that an elastic collision because it's pretty close. Like with particle physics, it's pretty close, so we use that. And so really, that's why I said that while there are 3 types of collisions, we only really deal with 2, elastic and completely inelastic. And that's my last one. Completely inelastic is when they stick together. An example of that would be like, let's see here. Aha, I got it. Let's say you have a bird and it's flying and someone shoots an arrow at that bird. It impales the bird. And then the bird and the arrow are one. And then, of course, they fall to the ground and the bird dies. I don't know why you'd shoot with an arrow, but why not? These are completely inelastic collisions because they stick together in the end. So, really, you got 2. Completely inelastic and elastic. A lot of times, this is simply just called inelastic. But it's really not inelastic. But a lot of people just refer to it as inelastic. So the terminology is a little bit... I wouldn't say vague. But approximated. There we go. Approximated. Alright, so this is from an old movie that I just haven't really taken it out. Anyways, let's say you have a 75-kilogram missionary. Gets into a scuffle with a movie producer's 100-kilogram bodyguard. He runs at 6 meters a second to the right when he collides with the bodyguard running at 3.5 meters a second to the left. After the collision, the missionary moves to the right at 0.5 meters a second. We want to figure out the final velocity of the bodyguard. Okay, so we're going to call the missionary M1. We're going to call the 100-kilogram bodyguard M2. Missionary V01. And the bodyguard is going to be V02. And then we have VF1. The velocity of the bodyguard or the missionary afterwards. So, this is where the principle of conservation of linear momentum applies. we take the sum of all of my initial momentums and set it equal to the sum of all of my final momentums. Meaning, we would have the initial velocity of 1, which is the missionary. Sorry, the initial momentum of 1, plus the initial momentum of the bodyguard is equal to the final momentum of the missionary and the final momentum of the bodyguard. Okay, so let's say what those are. Well, we know that p, lowercase p, is nothing more than the instantaneous momentum, mv. So I'll take m1 v01 plus m2 v02, and then it'll be equal to m1 vf1 plus m2 vf2. Okay, and we're trying to figure out vf2. We want to know the final velocity of the bodyguard. So I'm going to go ahead and move this over to the other side. m1 v01 plus m2 v02 minus m1 vf1 equals m2 vf2, and I'm going to divide by m2 just so I can have an equation just for this situation. Do I have to do it this way? No. Do I think it makes it a little bit easier? In my opinion, it does. Particularly when we get to the very end, the problems that we do. If I plug in numbers, I tend to screw it up. And you'll see what I'm talking about when we get to the end of this chapter. I think it's easier just to write, develop the situation, see what's going on, develop the formula from that, and then get it into one final, set it equal to one final variable, which is what we're doing. All right, so let's plug in some numbers and see what happens. I did not give myself that much room. Okay, but I can do this. All right, M1 was, we said, 75. And it says running to the right, so that's going to be a positive 6. Plus the mass of the bodyguard, that was 100 kilograms. And they were running to the left, so it's a negative 3.5 meters a second. And then minus M2, or M1, that looks like a 2. Let me go correct that before I screw something up. That definitely is an M1. Minus M1, which is the 75, and I'm going to have to drop my units to fit this in here. And then VF1, and the final velocity is a positive 0.5 because it says to the right. So it'll be a positive 0.5, although we are subtracting it. And then we divide that by the mass of the bodyguard, 100 kilograms. All right, calculating time. Let's do that. So I take 75 and I times it by 6, and I'm going to subtract 3.5 times 100. And then I'm going to subtract 75 times 0.5. And then I divide that by 100, and I get 0.625. So make sure I find the hits here. More or less makes sense. It's a positive, so it implies that it's moving to the right. The Mormon missionary is definitely smaller. It's at 75 kilograms, but it was moving quite a bit faster. And so basically he overpowers the bodyguard, because we know this because the velocity of the bodyguard ends up reversing direction. And because it reverses direction, well, he ends up losing. Now, people don't just run at each other and bounce off like ping pong balls. I'm fully aware of that. But it seemed to work with what I wanted to do, and I get tired of doing problems on billiard balls, because that's about the only good example out there. So basically, when you get to your end, you kind of look at it and say, okay, does that physically make sense? I'm like, yeah, I think it does. He was going pretty fast. He is smaller, but he was going a lot faster than the bodyguard. And the bodyguard doesn't move that fast in the other direction. Anywho. Okay. Let's do a slightly different type of problem. We have an angry 125 kilogram man running at 5 meters a second vents by tackling a 350 kilogram horse. The initial velocity of the horse is 1 meters a second in the opposite direction. What is the final velocity of the pair? So basically a situation where, like this one right here, where he tackles the horse. Not this. This is a horse collar tackle. This was banned in the NFL back in the early 2000s. Because when you look up horse tackle, you actually get that, and not this one, strangely enough. And where did I get this problem from? No clue. No clue. So we'll do with it. All right. So we have an angry man. Let's start with angry man. What are we going to start with? Well, we'll call angry man M1. And then its velocity, the man's velocity, is V01. The horse is going to be M2. And the initial velocity of the horse, we'll call it V02. Okay, so they stick together, so this is a completely inelastic collision. And just like last time, and I'll start off like this more or less every time, the sum of all of your initial momentums is equal to the sum of all your final momentums. Or in this case, it'll be M1 V01, M2 V02. So the momentum of the angry man, the momentum of the horse, and here's the fun part. So they stick together as one final momentum. And so it'll be M1 plus that's not an M2, all times a big VF for the big common velocity. This, I think your book, and I normally do this because I think it's handier, is just simply called big M, or a capital M. I often refer to it simply as big M. And just like this one is big VF, because that's what I've always done. And once again, I add them together because they form one cohesive unit. You can see that they're one cohesive unit as the horse falls, strangely. So, all right, what are our numbers? All right, well, the man was a very large man at 125 kilograms, but hey, large men get angry sometimes. And the large man's velocity was 5 meters a second, which is pretty fast pretty speedy for a guy that big. I need to erase this before I run into this. And then plus the mass of the horse, 350, which I thought was a little bit on the low side, but that's what went with it. And it said in the opposite direction, so I need to make this a negative 1 meters a second. And then that's equal to the sum of both masses, which will be 125 plus 350, so that's 450, 475. And I'm running out of room here, so I'm going to drop my units. Apologies for that. Big VF. So, in this case, I went ahead and plugged in numbers, mainly because I just did. But it's a really simple problem. I just need to divide everything on the left by the 475. So, let's go ahead and do that. So that's 125 times 5 plus a 350 times a negative 1. And that, strangely, 125 times 5. Okay, yeah, that's right. And then divide that by a 475, and it gets 0.57. 0.57? 0.58. 0.58. And it's a positive, so it implies it's in the direction of the man. Since the horse was running in the opposite direction. It's a lot heavier, but it was running a lot slower. Also notice something, that there is a kilograms in every single little piece right here. And so your only unit left is meters a second, so the units end up working out. So this is a slightly different problem, clearly. But this is a completely inelastic collision. Oh, I gave myself room, but I guess I didn't need it. Alright, collisions. While energy can be conserved in an isolated system, kinetic energy is not always conserved. And I've kind of mentioned that earlier. Kinetic energy is conserved in an elastic collision, but not in inelastic collisions. This leads to two different formulas that it's kind of a little bit beyond the scope of this class. But basically what we're going to do is we're going to kind of put together kinetic energy, the conservation of energy with the conservation of momentum, and kind of merge the two to kind of show what I mean. This is a classic problem. Um, it's a ballistics pendulum problem. Basically put, if you fire a bullet, it's going to go bam, and this thing is going to move up a certain amount of a height h. If you measure height h and you know the mass of your pendulum or the block and the bullet, you can actually work backwards to figure out the initial velocity, or the muzzle velocity of the gun. So this is how you can figure out how fast bullets are shot out of a gun. At least it was the original way of doing it. Hopefully I gave myself a page. I did not give myself a page. Oh, I can fit it in there. Okay, so we've got to break this up into multiple parts. And let me show you what I mean by that. What I do is okay, so first I break this up into part one. Part one is going to deal with the bullet and the block. So, bullet and block. Now, excuse me. What happens is when the bullet embeds in the block, it's going to be a completely inelastic collision, and then they're going to rise to a certain height h. This will be part two. So we'll have to do each part. And there's lots of different ways I can do this, but let's go ahead and start labeling things. We start with a block, and I'm actually going to call my block M2 since it's on the right of the bullet, which I will call M1. So consider the block to have a mass of 5.4 kilograms, the bullet's 9.5, and then we know the height h. So we don't really know a lot of information, and that's why we have to break it up into two parts. So if I just look at part one, what I've got is the momentum, P01, of my bullet, and then I have an initial momentum of my block, and then that's equal to one common final momentum because they stick together. It's a completely inelastic collision. So that means you have M1 V01 plus M2 V02 is equal to big M big VF. Well, what was the block doing initially? Nothing. It was completely stationary. So you have no momentum, initial momentum of block 2. So this formula is going to reduce to just being M1 V01 equals big M big VF. Well, we do know what big M is. It's the mass of the bullet in the block. We have that. And we do know what our initial, the mass of the bullet is. But what we don't know is the final velocity of the bullet in the block or the initial velocity of the bullet. So that's a little bit of a problem. But since we want to find the initial velocity of the bullet, I will solve for that. And that gives me V01 is big M, big VF over M1. That's as far as I can go. This is where part two comes in. Anytime I have two unknown variables, I need two equations, and so this is where it comes through. Now we're going to use the conservation of energy. Simply put, the moment the bullet embeds in the block, the final velocity from part one of the bullet and block is now going to equal the initial velocity in part two. I shouldn't have said VF2. I should have just said VF. Sorry. The final velocity in part one is going to be equal to the initial velocity in part two. That's why we had to set it up into two different things. And then just like our problems we did last, we have to figure out how high it rises and well, actually we know how high it rises, but what the initial velocity is based off of the height. And so we have to look at and say, okay, do we have initial momentum? Do we have initial kinetic energy? Do we have initial potential energy, etc.? Well, since the block and the bullet are at its lowest point, we do not have initial potential energy, but we know it's going to be kicked up to a certain height. So we do have initial kinetic energy. Over here, it's going to rise up to a point where it stops. So that means your final kinetic energy is going to be 0. And you do have final potential energy because it has potential to fall back down. And so what that means is, if you remember conservation of energy, it is K naught plus PE naught equals KF plus PEF. And we already said that we had no initial potential and no final kinetic. And if I expand that out, this K naught is going to become 1/2 of m V naught squared. And I need to make sure that I do one thing here. I need to use capital M because we're dealing with the mass of the bullet and the block, and we can't forget that. And then I will just make it a big V naught squared is equal to big M G H. Well, it really doesn't matter in this case because our masses end up canceling. And I'm going to go ahead and solve this for V naught. So V naught is going to be the square root of 2gh. Now, recall that that initial velocity, and this is from part 2, was equal to the final velocity from part 1. And so what I can do is I can take this little guy right here and I could substitute it in right there. So that's my next step. Let's do that. So that gives me V naught 1. That's a really big V naught 1. I need to make sure I have enough room here. Is equal to big M. And then for VF, I'm just going to substitute in square root of 2gh all over M1. We do have big M, that's the mass of the bullet and block. We do have M1, which is the mass of the bullet. We know the height, we know what gravity is. We can now figure out the muzzle, or rather the speed of the bullet as it hits the block. So let's do that. I think I have a little bit of room down here. I do. Alright, here we go. Big M. So there is 5.4 and 9.5 grams, so I gotta be careful with that. So it's gonna be 5.4 plus 0.0095. Oopsie. I'm gonna put kilograms on the outside here because I didn't put it for each of the individual units. And then square root of 2 times 9.8 times the height. Careful, this height is in centimeters, so I need to put 0.05 meters. The blocks generally don't rise that high. And then all divided by the mass of the bullet, which is 0.0095 kilograms. All right, calculations time. I'm going to start with the square root part. So 2 times 9.8 times 0.05, taking that to the square root, and then I multiply that by 5.4 plus 0.0095, and then I divide that by 0.0095, and I get 564 meters a second. So over 1,000 miles an hour, pretty fast. So this is an example of where we can use the conservation of energy and the conservation of linear momentum, put them together to solve problems where we have more than one missing variable. So when I put this all of my videos together, I realized that this slide and the video that went with it, or at least started on it, got cut in half, and I have no idea why. So I'm back to redoing this. Luckily, it wasn't really long, but center of mass. Center of mass is basically used in things like, and it's not center of mass, but if you want to find the population center of the United States, you would use something similar to a center of mass equation, meaning you would take your mass, the population of a city or town, multiply by its position, latitude and longitude, and then add each one up, and then divide by the sum of all the masses of the population. So that's how we see that the population center just kind of keeps moving further to the west as time goes on. So that's kind of at least an application of, say, a center of mass. Or center of mass is also important when you want to balance something, particularly when we get to, like, chapter 10, when we start doing static equilibrium type problems. That's when center of mass is pretty important. Also, velocity of center of mass you can find as well, which is important because in things like elastic collisions, your velocity of center of mass is actually going to be conserved and stay the same. So two different equations. One thing I'd like to talk about is the center of mass equation itself and like different scenarios. So let's take a scenario that, I don't know. Let's say that the second mass is 0. Well, if the second mass is 0, that's going to be m1x1 plus 0 over m1 plus 0. M1 cancels, and your center of mass is equal to the x. That's not a, that's supposed to be a 1, by the way. Is equal to x1, meaning the center of mass is exactly at the object, the only object remaining. So mathematically, that part makes sense. Likewise, we could do other things that we can come up with. Let's say, okay, so we have m2 equals 0. Let's make an assumption of, let's see, let's go ahead and do this one. What if m1 was twice the size of m2? That would give me m1, well, instead of m1, I'm going to plug in 2m2 x1 plus m2 x2 over 2m2 plus m2. M2's cancel. And that's going to give you, rolling down here, 2x1 plus x2, then divide that by 3. What this means is you can kind of tell just by looking at this that the center of mass is definitely going to be closer to your x1 since it's heavier and it's heavily favoring it to pull towards it, at least by a factor of 3, which would physically make sense. If you made, let's say your x1, kind of draw this out here, is at the origin or 0, then it would be x2 over 3. So it would be the distance to the m2 in this case, but it'd be 1/3 of it. So it actually works out to be right where the picture is, roughly. It'd be 1/3 of the way through, which makes sense because it's twice the mass, so it definitely should be closer to it. So you can use this equation to kind of mathematically verify different center of mass situations, and most of them will make sense when you start to think about it. That's about as deep as we really go with center of mass. It's really, if you notice, sorry I haven't mentioned this before, but I meant to, is that the velocity of center of mass is nothing more than a completely inelastic collision. And so that's kind of the direction that this is going. Because notice on the bottom here, this is big M, and this is momentum 1, momentum 2, and then so forth. Okay, that is, I'll cut this slide and insert it in, then I'll start the next slide. Alright, let's do an example problem. These are my old rats I used to have years ago, dx and dt. If you took calculus, and you know what if you took calculus, you will know that dx over dt is velocity. I don't know why we named them that, but we did. So we have two rats located 5 meters apart. DT is around 700 grams, while DX is around 400 grams. Moments later, DT is running at 5 meters a second to the right, while DX is 4.2 to the left. What is the center of mass between the two rats before they take off, and what's the velocity of center of mass? So they're located 5 meters apart. So basically, you have to put somebody at the origin. I generally will put DT there. Your book problem will generally say who's going to be at the origin. So DT is going to be at x1 equals 0. And so I take, okay, M1, which is 0.7 kilograms, times x1, which is 0, times dx. Dx is lighter, around 0.4 kilograms. And it was 5 meters away. Divided by the sum of both masses, so that's 1.1 kilograms. Kilograms cancels. Yay. Well, that wouldn't matter because that one's 0. Don't know why I did that. So I'm going to take 0.4 times 5 and divide that by 1.1, and it gets 1.8, which is closer to dt, because dt is larger. Meters, not kilograms. Try that again. So that makes sense. Then for the velocity of the center of mass, it's a rather easy problem. I see that dt is 700 and moving at 5 meters a second to the right. So I'm going to take 0.7 kilograms and a positive 5 since it's going to the right, plus dx, dx is 0.4. Dx is moving at 4.2 to the left, so I make that negative. Divided by the sum of their masses, 1.1 kilograms. So I take the 0.7 times 5 plus the 0.4 times a negative 4.2, closing parentheses, dividing that by 1.1. It's going to give you 1.65. So this is probably some of the easiest stuff you have this chapter. As to be compared with the hardest thing, which is what we do next. All right. Let's say you have a neutrino. A neutrino is a small subatomic particle of the lepton class. Leptons meaning they are not made up of quarks, if you know what those are. But basically, neutrino is small, generally indicative of a nuclear reaction. How small? It's around 1/500,000th of the mass of an electron, and that's kind of an estimate because they're still trying to, well, at least they're really close to understanding the mass of an neutrino. But in any case, I just approximated it. And let's say it's shot at an electron. An electron is small, around 1/1000th-ish the mass of a proton. And, of course, a proton's really small, too. So, yeah, these are all very, very small things. Anyways, we shoot the neutrino at an electron. We assume the electron's initially stationary. And we also assume it's along the x-axis. I always forget to put that in there, but that's true. So, basically, I'll draw a picture here in a second. After the collision, we see the electron moves off at 5 degrees at 4,000 meters a second. The final velocity of neutrino we can measure is 5 million meters a second at -70. We want to figure out the initial velocity of the neutrino. All right, so I need to draw this out. Here is my neutrino. It's generally represented by a nu, and we'll call this an electron neutrino. A little small little ball, and it's being shot along the x-axis, and it hits a much larger electron, and the electron is going to move off at a very small angle of 5 degrees. So this will be my electron, and the the neutrino, sorry about that, is going to move off at a much larger angle. Oh wait, we represent this by straight lines. There we are. At -70. Okay, and this is my neutrino. Okay, so this is just like the force type problems. We draw a picture, label everything, and then from that we figure out our unknowns, figure out our equation, etc. I don't know the initial velocity of my neutrino, which I'll call Vaughn. We do know this velocity, and that was 4e3? 3. Yeah, 4,000. And we know that this was 5 times 10 to the 6, I believe. Let me double check. Yeah. So, based off of that, I kind of have to figure out what's going on. Well, this is similar to our previous problems of conservation of linear momentum, and that the sum of all of your initial momentums in the x direction is equal to the sum of all your final momentums in the x direction. So we're starting with x. Okay, well then that means let's take the momentum, or let's write this out bigger for the first time. So the initial momentum of my neutrino in the x direction, Ponx, plus the initial momentum of my electron in the x direction, Pox, must be equal to the final momentum of my neutrino in the x, Pfennigs, plus the final momentum of my electron in the x direction, Pfix. Okay, so very similar process, except now we have to do it with respect to x and y, which does make it a little bit trickier. Okay, well, one other thing before I get started. I made this a little bit easier because the mass of an electron is around 9.11 times 10 to the negative 31st kilograms. That's a lot to write. So I expressed the mass of the neutrino with respect to the electron. And so for my mass of the neutrino, Mn, I'm just going to call it 1 over 5e5 me. That will make it easier, I promise. So that's what we're going to start with. So I take my mass of my neutrino, which is 1 over 5e5 me, times the initial velocity in the x direction, or the horizontal direction, of my neutrino. But I'm just going to put v naught n, because I know that it's only in the x direction since I defined it earlier as traveling along the x-axis. Okay, that makes it a little bit easier. This gets really easier. The electron's stationary, so the initial momentum is going to be 0. Yay. Then that's equal to your mass of your neutrino, so 1 over 5e5 me, remember, because that's 1/500,000th of it, times the final velocity of my neutrino, and I want the horizontal component of it. My neutrino's horizontal component is right along this dashed line right here, so that's going to be the cosine of negative 70. And it doesn't really matter that it's negative or positive. It will for the y, but in the x it doesn't, because the cosine is positive in quadrant 4. Okay, there's that. Then the mass of my electron times the final velocity of my electron, and then we have to find its component, which is also going to be cosine. But its angle is not negative 70, its angle is 5. Now, the reason that I express it in terms of the electron is if I do that, I can cancel out all of my MEs, and I don't have to worry about the fact that it's 9.11 times 10 to the negative 31st. Makes it a bit simpler in the calculations. Then looking at that, I'm trying to solve for v naught n, right? I want to know the initial velocity of my neutrino. But I don't, I do know the, sorry, erase that. I do know the final velocity of my neutrino, but I don't know the final velocity of my electron. And of course, I don't know the final initial velocity of my neutrino. So I have two unknowns. So anytime you have two unknowns, you need two equations. Different ways that I can do this, but I'm just going to go ahead and solve this for the initial velocity of neutrino. And then start with the vertical, doing the y. So I'm just going to multiply everything by 5e5. That's going to give me VFN, the final velocity of my neutrino, cosine of negative 70, plus 5e5 VFE cosine of 5. Okay, so basically, I know what VFN is, and I can plug that in later, and I will. But for now, I'm just going to leave it there because then it just gets bigger. So we'll stick with that. Now we're going to do the Y. See what's going on up and down. And this, in some regards, is a little bit easier. In fact, I think in most regards it is. Okay, so it's easier because the initial momentum of my neutrino in the Y, since it was completely confined to go left and right, it's 0. Yay. Plus, electron wasn't moving, so it doesn't matter. No momentum. 0. Oh, this is good. Then we have the... then we'll have 1 over 5e5. So remember, we got to find the mass of our neutrino. So I take it with respect to electrons. Electron, me, times the final velocity of my neutrino. And now we sine negative 70. Because we need the vertical component that's going down right there. Plus me, final velocity of my electron, VFE, sine of 5. Haha. Okay, I said this is easier in some regards. It is, because we can actually use this to solve for my final velocity of my electron, and then I can plug it in up here to figure out the initial velocity of my neutron. So we'll go ahead and do that now. I'm going to, let's go ahead and start solving it. Notice one other thing I forgot to do. I can cancel my MEs. That's going to make it a little bit easier. And I'm going to solve this now for the final velocity of my electron. It's going to give me negative 1 over 5e5. I'm moving this to the other side. Final velocity of my neutrino was 5 times 10 to the 6th meters a second. Sine of negative 70. And then all that is divided by the sine of 5. I have a second page here and I'm running out of room. I know. All right. So, negative 1 divided by 5e5 times 5e6 times the sine of negative 70. Boom. Divide that by the sine of 5. It's going to give me 107. We're just going to say 108. Not very fast. But remember, it's 500,000 times more massive. So, yeah, it may not move very fast. Okay, so now that I know that, I'm going to plug it into my V naught N equation up here. The final velocity of my neutrino was 5e6 meters a second. Cosine of negative 70. Plus 5e5. Final velocity of my electron was 108. Cosine of 5. So now we have everything we need to solve the problem. So let's do that. All right, so let's take 5 times 10 to the 6, so 5e6 times the cosine of negative 70. Plus... we'll do 5 times 10 to the 5th times 108 times the cosine of 5. And that gives me a very large number. But I should have done this right. That gives me, let's see here, 1, 2, 3, 4, 5, 6, 55 million. Looks like 55,500,000. Or 5.5 E7, roughly, meters a second. Couple things. If I ever give you a problem like this, like on your written homework, your velocity cannot be greater than ever 3 times 10 to the 8th meters a second. That is a no-no. That'll hold really well in physics too. That's the speed of light. Nothing could exceed the speed of light. Occasionally I'll make up a problem and I'll do it and I'm like, oh crap, I gotta remember this speed of light. Nothing that we know of can move faster than the speed of light in a vacuum. You can, and when you're in a substance, sometimes it can get actually higher than that. But generally, in a vacuum, that is the speed. So that's kind of a way of knowing you did something wrong if you get a value larger than that. If I give you something like this, so this one's a little bit easier, I think, than the next one that I do, just because of the y components being all momentums being 0 initially. So that kind of helped. But in any case, it's a two-step process. You need to split it up into your horizontal and vertical components. And that's what we'll do now. We have a 100-gram pool ball traveling at 10 meters a second at 10 degrees, and it collides, I didn't really word that really well, with a 100-gram pool ball traveling at 5 meters a second in the same direction at negative 10 degrees. They collide in an inelastic collision, so they stick together. Completely inelastic collision. What is the final velocities? All angles are measured relative to the x-axis. So let me draw you a little picture of what's going on here. We have a pool ball, and it's traveling, let's see here. I'm going to come down here a bit. Give me a little bit more room. Let's draw ourselves an x-axis right here. You know what I can do? And you said, oh, you should have been doing this all the time. And you're probably really right. Here's my x-axis. This red line. Oh, God. Why did it take me so long? All right. So here's my pool ball. Let's draw my pool ball here. And it's traveling at a negative... Dang it. Negative 10. Ha ha ha. I see what you're saying. Up here. So basically put... let's do this a little bit better. I want to be consistent. It's traveling this angle right here is negative 10. That's what it means. Now, it's colliding with a pool ball that is at a positive 10. So let me draw a ball right around here. There. I did need both of them, but I drew it backwards initially. All right, so basically they're coming from two different but equal and opposite angles. What's not equal and opposite is the velocity. We have one that's traveling, the one that's traveling at 10 degrees is going to be 10 meters a second. And one is traveling at 5. So really with this one, as long as you label the correct ones being positive going with 10 and the negative going with 5, you should be able to solve it pretty easily. And basically, it collides in an inelastic collision because we covered them with superglue, because we could. And it becomes one big ball. Okay, that's really not accurate, so let's just do this. 2 balls become 1, and we want to figure out where it's going to go from there. Okay, so it's the same type of setup. We have X and Y components, so that's why this one's a little bit harder. But I will start with what's going on with respect to X. So I need to find all of my momentums. One other thing that I'm going to do, I'm going to erase this real fast here and say that M1 is equal to M2, which is equal to M. Why am I doing that? Because notice I gave the pool... I mean, if they're pool balls, they're usually identical masses, right? I mean, they might vary by a couple fractions of a gram. But for our purposes, we're just going to keep them the same mass. And if I call it all M, I could cancel at least the masses out, and it'll make my calculations a little bit easier. So that's what we're going to do. Okay. All right, so let's start with... Okay, we're going to call Who's the first one that we came up with? 10 degrees? All right, so the bottom one's going to be 1. Top one's going to be 2. All right, here we go. So with respect to the x, or the horizontal, we have m1, and it does have an initial momentum, so it's going to be m1 times the initial velocity of ball 1, so v01, and then we need its component, so we want the cosine, so we get this horizontal side, cosine of 10 degrees plus m2, and I need to erase this real fast. I'm going to totally run into my picture. There we go. m1 v01 cosine 10 plus m2 v02 cosine of negative 10. So they're both going to be in the right direction because they're quadrant 1 and 4. And then that's equal to big M, which I would... Oh, I said we call these M and I didn't. Whoopsie. Let's go ahead and do that now. I could call it big M, but since I know they're added together, I'll just say 2M, right? Because it's our big mass all put together, okay? And then it's going to have one final common velocity, VF, but it will have a component that we don't know. So VF cosine of theta. Because we don't know what its component's going to, or what its angle's going to be. So, all right. So this is basically why this is a two-step, or rather a two-equation problem, is because we know we can cancel out our m's. Let's start with that. We know our initial velocities and we know our initial angles, but the reason it's two-stepper is because we don't know the final velocity and the angle it moves off at. So that's why we have to do what's going to go in the y. Different ways that we can do this, but in my opinion, solving for theta is just ridiculous. I've never tried it that way, but I just can't imagine that being very easy. So what I'm going to do is just move my cosine theta to the other side and just write down v01 cosine of 10 plus v02 cosine of negative 10. Get my little line here. Undo my line over the cosine of theta is equal to our big final velocity. All right, let's do what's in the y. All right, so that's going to be m v01 sine of 10 plus m v02 sine of negative 10 equals, same thing, they stick together, so double the mass, the final common velocity, sine of theta. Okay. The only reason, FYI, that I chose cosine for x is because, in general, since we've been drawing the pictures like this, the cosines generally have tended to be your horizontal values, and they usually are. So that's a good rule of thumb. All right. Couple different ways that I can do this, but looking at it right here, I'm just going to go ahead and cancel my masses. And I think what I'm going to do is take this now and sub this in here. And it's about to get crazy. It's about to get crazy. I think I can fit it here. All right, here we go. That gives me v01 sine of 10 plus v02 sine of negative 10. Put parentheses around that so I make sure I see my negative here. And that's equal to 2. And then that'll be v01 cosine 10 plus v02 cosine. I don't know why I wrote sine. Sorry about that. Cosine of negative 10. And that looks almost like a 1, so I'm going to redraw that. There we go. And then that's all over the cosine of theta times the sine of theta. Well, sine over cosine is going to give me tangent. So that's going to make things a little bit easier. So let's simplify this a hair. And so that's going to give me V naught 1 sine of 10 plus V naught 2 sine of negative 10 is equal to, and that's going to give me 2 tangent theta, and then what's left in parentheses, which is V naught 1 cosine of 10 plus V naught 2 cosine of negative 10. And then there's nothing left in, underneath the denominator because we pulled that out as tangent. So then I'm just going to divide the left side by 2 and then this little guy over here. So that's going to give me V naught 1 sine of 10 plus V naught 2 sine of a negative 10. And then line. And then that's going to give me 2, and I'm just going to distribute my 2. 2 V naught 1 cosine of 10 plus 2 V naught 2 cosine of negative 10 is equal to the tangent of theta. Okay. Now, you might be thinking, if this looks confusing, why am I not plugging in numbers? Because if I plugged in numbers, it would not really fit on this page, number one. Number two, it does tend to minimize errors if you solve it like this without plugging in numbers first. And also, when you do it like this, it also helps you to see patterns, like how you can cancel out the masses and things like that. So that's kind of why I like it. While you might be tempted to try to cancel out some of these sines and cosines, you can't, so it doesn't really work. Not on this one. You just got to plug in numbers, which is our last step, and then take the inverse tangent of it. So what I'm going to do is just find that number first, and then we'll just take the inverse tangent of it. So let's plug in what it actually is. V naught 1 we decided was a 10. So there is 10 meters a second sine 10 plus 5 meters a second sine negative 10. And then 2 V naught 1, so that's, I'm just going to write 20 meters a second because 2 of V naught 1 cosine of 10 plus 2 of V naught 2, so that's 10 meters a second. Sorry, I keep writing the wrong one. Cosine of negative 10. It's a lot harder to catch myself writing the wrong thing. Like I normally do on a chalkboard or a marker, I can catch it a lot faster. But with this thing, I have to hit a different button in order to make it delete. So that's why it looks a lot worse on here than in person, strangely enough. All right, let's just solve it. See what that number is. All right, here we go. 10 times sine 10 plus 5 times sine of negative 10. Let's put that in parentheses so it doesn't get itself confused. Divided by, lots of parentheses here. 20 times the cosine of 10 plus 10 times the cosine of negative 10, closing parentheses, closing. I think 3 parentheses there. And I'm getting 0.029. And so I take the inverse tangent of that, and I get 1.68. Degrees. All right, so now that we have my angle, I'm going to go back and figure out my final velocity by using what this equation is in parentheses. So let's do V naught 1 cosine of theta 1. So V naught 1 cosine of theta 1. V naught 1 was 10 meters a second. Cosine of theta 1 was going to be 10 plus V naught 2, 5 meters a second. Cosine of negative 10, all divided by the cosine of 1. That's bad. 1.68. Almost wrote meters a second. Let me make sure that's right. Yeah. Yeah. All right. 10 times the cosine of 10 plus 5 times the cosine of negative 10. Divide that by the cosine of 1.68. It's going to give me 14.92. We'll just say 14.9. So the velocity is more or less reasonable. It kind of stays on track, but it turns into right around 15 meters a second. And that is it for this chapter. You're going to have one of these probably on the test, and you'll definitely have one of these on the written homework. So make sure you know how to do these. And I think I have some practice problems posted. I think I even have a few in there. Maybe I'll make up more. We'll see. All right. That is it.